Welcome to the Neuralink Show and Tell. So we've got an amazing amount of new developments to share with you that I think are incredibly exciting, as well as tell you about the future of what we're planning to do here. It's and now this is meant to be a technical podcast, sort of like a. I'm going to provide an overall summary, and then we're going to have a number of members of the Neuralink team come in and give a deep technical overview of the various areas. So so let me move forward with the overall summary. Now, some of the things I'm going to say are things if you've been following Neuralink, you've already heard before, but for a lot of people out there, they've no idea what Neuralink does, and so I will be a little bit repetitive of things you may already know, but that others do not. So, the overarching goal of Neuralink is to create ultimately a whole brain interface. So a generalized input-output device that, in the long term, literally could interface with every aspect of your brain, and in the short term, can interface with any given section of your brain and solve a tremendous number of things that cause debilitating issues for people. So. So our long term is I'll talk a little bit about our long term goal. It's going to sound a little esoteric, but it was actually the sort of my prime motivation, which was, what do we do about AI? Like, what do we do about artificial general intelligence? If we have digital superintelligence that's just much smarter than any human, how do we mitigate that risk? At a species level, how do we mitigate that risk? And then even in a benign scenario where the AI is very, very benevolent, then how do we even go along for the ride? How do we participate? And the conclusion, the thing that the biggest limitation in going along for the ride and in aligning AI, I think, is the bandwidth, the how quickly you can interact with the computer. So we are all already cyborgs in a way, in that your phone and your computer are extensions of yourself. And I'm sure you found, like, if you leave your phone behind, you end up tapping your pockets, and it's like having missing limb syndrome. Like, where the phone is, leaving your phone behind is kind of like a missing limb at this point. You're so used to interfacing with it. You're so used to being a de facto cyborg. So what's the limitation on a phone or a laptop? The limitation is the rate at which you can receive and send information, especially the speed with which you can send information. So if you're interacting with a phone, it's limited by the speed at which you can move your thumbs, or the speed at which you can talk into your phone. This is an extremely low data rate. Maybe it's like 10, optimistically 100 bits per second, but a computer can communicate at gigabits, terabits per second. So this is the fundamental limitation that I think we need to address to mitigate the long-term risk of artificial intelligence, and also just go along for the ride. And but like I said, that's an esoteric explanation that I think will appeal to a niche audience, some of whom may be here, And that's a very difficult problem. So even if we do not succeed with that problem, I think we are confident at this point that we will succeed at solving many brain injury issues, spine injury issues along the way. So So anyways. So actually we have Justin Roiland in the audience. Hi, Justin.
So it's a little Rick and Morty reference here. Um, this great Rick and Morty episode about intelligence enhancement of your dog, and what's the worst that could happen? So anyway, Rick and Morty, I recommend it. So so you want to be able to read the signals from the brain. You want to be able to write the signals. You want to be able to ultimately do that for the entire brain, and then also extend that to communicating to the rest of your nervous system if you have a sort of a severed spinal cord or neck. So now this video is now 18 months old. So this is Pager, who is playing monkey mind pong. So this is Pager has a Neuralink implant in this video, and the thing that's interesting is that you can't even see the neural implant. So we've miniaturized the neural implant to the point where it matches the thickness of the skull that is removed. So it's essentially it's sort of like having an Apple Watch or a Fitbit, replacing a piece of skull with like a smartwatch, for lack of a better analogy. So you can see, he looks pretty, he's normal. And I think that's pretty important. If you have a Neuralink device, like I could have a Neuralink device implanted right now, and you wouldn't, you wouldn't even know. I mean, hypothetically, maybe one of these demos, in fact, one of these demos I will. Yeah. So yeah. Anyway, so here's I mean, first of all, it's kind of wild. Hey, monkeys can play Pong. They can actually play Pong if you give them a joystick. So Pedro first learned to play Pong with a joystick. So I'm like, that was novel. It's like I didn't know monkeys could play Pong, but they can. And then so we first trained Pedro to play Pong with a joystick. Then we took the joystick away and have the Neuralink, and now he's playing It's a telepathic video games essentially. So what we've been doing since then is we've been on the very difficult journey from prototype to product, and I've often said that prototypes are easy. Production is hard. It's really, I'd say, 100 to 1,000 times harder to go from a prototype to a device that is safe, reliable, works under a wide range of circumstances, is affordable, and done at scale. It's insanely difficult. I mean, there's an old saying that that it's 1% inspiration, 99% perspiration, but I think it might be 99%, or 99.9% perspiration. The best example I could give of an idea being easy, but the execution being hard, is going to the moon. It's the idea of going to the moon, easy. Going to the moon, very hard. So, we've been working hard to be ready for our first human. And obviously, we want to be extremely careful and certain that it will work well before putting a device in a human. But we've submitted, I think, most of our paperwork to the FDA, and we think probably in about 6 months we should be able to have our first Neuralink in a human. So. But as I said, we do everything we possibly can to test the devices before, not even going into a human, before even going into an animal. So we do benchtop testing, we do accelerated life testing. We have a fake brain simulator that has the texture and it's like emulating a brain, but it's sort of rubber. And so before we would even think of putting a device in an animal, we do everything we possibly can with rigorous benchtop testing. So we're not cavalier in putting devices into animals. We're extremely careful, and we always want the device, whenever we do the implant, if it's in a sheep or a pig or monkey, to be confirmatory, not exploratory, so that we've done everything we possibly can with benchtop testing, and only then would we consider putting a device in an animal. We'll actually show you a demo later today in a few hours, really, of implanting in a brain proxy. And if anyone in the audience wants to volunteer, we have the robot right there. So let's see, and since the page of demo, we've expanded to work with a troop of 6 monkeys. We've actually upgraded Pager. They do varied tasks, and we do everything possible to ensure that things are stable and replicable, and that the device lasts for a long time without degradation. So, and what you're seeing there is, it looks like the Matrix, but that's actually that's a real output of neural signals. So that's not a simulation or just a screensaver or something. Those are actual neurons firing. That is what one of the readouts looks like. And here you can see Sake, it's one of our other monkeys, typing on a keyboard. But now this is telepathic typing. So to be clear, he's not actually using a keyboard. He's moving the cursor with his mind to the highlighted key. Now technically, we can't actually spell, and so I don't want to oversell this thing, because that's the next version. But what's really cool here is Sake the monkey is moving the mouse cursor using just his mind, moving the cursor around to the highlighted key, and then spelling out what we want to spell. But and then so this is something that could be used for somebody who's say quadriplegic or tetraplegic human, even before we make the spinal cord stuff work, is being able to control a mouse cursor, control a phone, and we're confident that someone who has basically no other interface to the outside world would be able to control their phone better than someone who has working hands. So. Yeah. And I mentioned upgradability. Upgradability is very important because our first production device will be much like an iPhone 1. And I'm pretty sure you would not want an iPhone 1 stuck in your head if the iPhone 14 is available. So it's going to be, being able to demonstrate full reversibility and upgradability, so you can remove a device and replace it with the latest version, or if it stopped working for any reason, replace it. That's a fundamental requirement for the device at Neuralink. And I should say both Sake and Pager were upgraded to our latest and greatest implants. So that's been really over a year and a half now that Pager's had for the first implant and then the upgraded implant. So this is a very good sign that it lasts for a long time with no observed ill effects. I think it's also important to show that Sake actually likes doing the demo and is not like strapped to the chair or anything. So yeah, so the monkeys actually enjoy doing the demos because and they get the banana smoothie, and it's kind of a fun game. So. I guess Smart Filmmakers, like, we care a great deal about animal welfare, and I'm pretty sure, like, our monkeys are pretty happy, you know. So as you can see, a quick decision maker on the fruit front. So for our, the first two applications we're going to aim for in humans are restoring vision. And I think this is, like, notable in that even if someone has never had vision ever, like they were born blind, we believe we can still restore vision. Because the visual part of the cortex is still there. Yeah, even if they've never seen before, we're confident that they could see. And then the other application being in the motor cortex, where we would initially enable someone who has no ability, almost no ability to operate their muscles, you know, sort of like a sort of Stephen Hawking type situation, and enable them to operate their phone faster than someone who has working hands. But then obviously even better than that would be to bridge the connection. Take the signals from the motor cortex, and let's say somebody's got a broken neck, then bridging those signals to Neuralink devices located in the spinal cord. So we're confident there are no physical limitations to enabling full body functionality. I mean, as miraculous as it may sound, we're confident that it is possible to restore full body functionality to someone who has a severed spinal cord. So, yeah. So, yeah. All right. And then I want to emphasize again that the primary purpose of this update is recruiting. A lot of times people think that they couldn't really work at Neuralink because they don't know anything about biology or how brains work. And the thing that we really want to emphasize here is that you don't need to, because when you break down the skills that are needed to make Neuralink work, it's actually many of the same skills that are required to make a smartwatch or modern phone work. So it's sort of, you know, software, batteries, radios, inductive charging, and you know, as well as things that are specific to us, like animal care and clinical and regulatory matters. Obviously, machine learning, that phrase is used a lot. But we obviously need to interpret the signals from the brain, which is a biological neural net, and the best thing to interpret a biological neural net is a digital neural net. So this is, if there's one message I want to convey, it is that if you have expertise in creating advanced devices like watches and phones, computers, then your capabilities would be of great use in solving these important problems. That's more than anything the message I want to convey. Let's see. Yeah. So with that, I guess, DJ. DJ's was on the founding team of Neuralink and has made immense contributions to the company, as have many of the others who will present. But I want just to thank DJ for his immense contribution to Neuralink and all right, cool, thank you.
Thanks, Elon. When I moved from South Korea at age 13 and needed to learn a new language to communicate, I wondered whether there are better and more effective means of communicating my thoughts to the outside world. And watching Neo learn Kung Fu in The Matrix, I remember thinking, wow, I want to work on that, work on making that possible. And today, I believe that this is a tractable engineering challenge. Since everything about your intentions, your thoughts, and your experiences are all in your brain, encoded as firing statistics of action potentials, if you're able to put electrodes in the right places with the right sensing and stimulation capabilities, this and many other applications that Elon talked about are possible, and we can help a lot of people. I'm incredibly excited to be working on this ambitious yet important mission to make that future a reality here at Neuralink. And I'm also incredibly honored to be working with some of the brilliant colleagues, scientists and engineers across many engineering disciplines, to work on this intersection of biology and technology. You'll hear from several of them today to learn about the breadth of technical challenges we face and our progress in the last year. And I think you'll find that for most of these challenges, as Elon mentioned, you don't need a prior understanding of how the brain works, and that a lot of what we do is applying engineering first principles to biology. So how do you create a high bandwidth generalized interface to the brain? From day one, we focused on a set of foundational technologies that are safe, scalable, and capable of accessing all areas of the brain. These three axes, safety, scalability, and access to brain regions, really form the basis for how we engineer products here at Neuralink. Safety, because we want to make our devices as well as the installation as safe as possible so that we can drive the adoption of this technology. And scalability, because as we make our devices safer and more useful, more people will want it. And with scale, we also want to make it more affordable. And access to brain regions so that we can expand the functionalities of our technologies. So our first steps along these dimensions for our device is what we call the N1 implant. It's a size of about a quarter, and it has over 1,000 channels that are capable of recording and stimulating. It's microfabricated on a flexible thin film arrays that we call threads. It's fully implantable and wireless, so no wires, and after the surgery, the implant is under the skin and it is invisible. It also has a battery that you can charge wirelessly, and you can use it at home. So similarly, for implanting our device safely into the brain, we built a surgical robot that we call the R1 robot. It's capable of maneuvering these tiny threads that are only on the order of a few red blood cells wide, and inserting them reliably into a moving brain while avoiding vasculature. It's quite good at doing this reliably. And in fact, because we've never shown an end-to-end insertion of a robot in action, we're going to do a live demo of the robot doing surgery in our brain proxy. So who wants to see some insertions? So here it is. That's our R1 robot with our patient Alpha, who is lying comfortably on the patient bed. This is what we call the targeting view. So what you're seeing is this is a picture of our brain proxy. And the pink represents the cortical surface that we want to insert our electrodes into. And the black represents the vasculatures that we want to avoid. And what you're seeing is these hash marked with numbers that represents where we intend to put each of our threads. So should we see some insertions? So this is another view real quick. On the left is the view of the insertion area. And on the right, what the robot's going to do is it's going to peel the array, the threads, one by one from its silicon backing and insert it into the targets that we predetermined in the targeting view. So there you go. That's the first insertion. So we're going to see a couple more insertions. The whole process of inserting about 64 threads in our first product is going to be around 15 minutes for this robot. So yeah, there's a second one that went in, and we're going to do a third one. There you go. And then that's going to go in the background, and we'll come back to it in the later part of the presentation. And as Elon mentioned, we've been working very hard to go from prototype to building product. As part of this, one of the things that we did is to move our device manufacturing to a dedicated facility in Austin for scale-up manufacturing. And what's important to highlight, and is evident in this clip, is that it's very typical for us to have our engineers who design also work on the physical manufacturing line to build and debug. And this has been extremely, extremely critical in reducing our iteration cycle time. And we've also scaled up our surgery. So we now have a dedicated, our own OR, in fact, a double OR in Austin. And this is just a stepping stone before we eventually build our own Neuralink clinic. So with this product, N1 and R1, our initial goal is to help people with paralysis from complete spinal cord injury regain their digital freedom by enabling them to use their devices as good as, if not better, than they could before the injury. And as Elon mentioned, over the last year, this has been the central focus of the company. And we've been working very closely with the FDA to get approval and to launch our first in-human clinical trial in the US, hopefully in the next 6 months. So hopefully this gives you a good overview of our product. For the next hour, we're going to go through a deep technical dives on these topics to tell you about our technical challenges, share some of our progress, and preview what's coming next. So with that, over to Nir from my team, who's going to talk to you about neural decoding.
Thank you, DJ. And hey, everyone. My name is Nir Evan-Chen, and I'm the head of Brain Interfaces Applications. Our goal is to enable someone with paralysis control a computer, as well as me, or even better. We'd like to provide fast and accurate control with all the functionality of computers that works anytime, anywhere. So I'm very excited to show you how we're using the N1 device with our software and algorithms to achieve this. Last year, we shared with you a video of Pedro the monkey controlling a computer cursor with his brain. So how do we do that? Just a brief reminder. First, we record his neural activity from the motor cortex using the N1 device. We can record from over thousands of channels while he's playing with the joystick. Then we can train a neural net that predicts the cursor velocity from the patterns of his neural activity. With this decoder, he can then control a cursor just by thinking about it, without even moving the joystick. He can play with this decoder a variety of games, also a grid task, where he's moving the white dot towards the yellow target. Every time he gets one, he receives a drop of his favorite smoothie. And he chooses to play this game every day. Here you can see his performance from early 2021, around the time we released the previous demo. It's quite accurate, but it's a bit slower than what we would like. And cursor control is the foundation for interacting with most computer applications. So since then, we've been working to improve cursor speed and accuracy. As you can see, it's much, much faster, almost twice as fast. However, it's still a bit slower than what I can do. So we are working on creative ways to improve that. Now, speed is not enough. You want a full set of functionalities. And for decades, most software was built for mouse and keyboard control. And it doesn't make sense to reinvent this entire ecosystem for brain control, at least for now. So we are working and we are designing mouse and keyboard interfaces for the brain. The way we do that is by training Pager and his friends on a variety of computer tasks, and then designing algorithms to predict their behavior. Here you can see a few examples of tasks in different phases of monkey training. For example, left and right click, click and drag, cursor typing, swipe typing, handwriting, and even hand gestures. Now, interacting with computer is bidirectional, and feedback is very important. I like when I click on a button and I can physically feel the button being pressed. When a potential N1 user will attempt to click, they won't be able to feel it. An example of how we are addressing that is by providing a real-time visual feedback that represents the strength of the neural click by changing the color of the cursor. Just by typing on a physical keyboard is much faster and easier than typing on an iPad keyboard. This will make the brain control much faster and easier to use. Typing, one of the most important functionalities. So you already seen this message, and I want to show you the behind the scene of how this message was created. And here you can see again Saki using the virtual keyboard, typing this message. This virtual keyboard is similar to the one I use on my phone. And with the speed and accuracy that we achieved so far, typing on a virtual keyboard is already fast and easy. However, I never use a virtual keyboard when I type on my computer, because it covers my screen, and it's also much slower than what I can do with my 10 fingers. We can do better. For example, a group from Stanford asked a person to imagine handwriting letters. Then they decoded the letters from his brain activity. Using this approach, they were able to speed up the typing rate. We started this project with our monkeys, but of course they don't know how to write. So to mimic writing, we trained Ranger, one of our favorite monkeys, to trace digits on an iPad. Here you can see him tracing the digit 5 and the digit 2. Then we recorded his neural activity with the N1 device. But now, instead of decoding the cursor velocity, we decode in real time the digit that he's tracing on the screen. We had two main takeaways from this project. One, that monkeys are awesome and can learn very, very complex tasks. The second one, that although it can increase the typing rate, it requires hundreds of examples and samples of each of the digits and the characters we wanted to classify. This would not scale. The way we are solving that is by indirection. Instead of decoding directly the digits, we first decode the hand trajectory of on the screen. And then, when we decoded the hand trajectory, we can use any off-the-shelf handwriting classifier to predict the digit and the characters. For example, classifiers that are trained on an MNIST dataset. Why it's so important? It's important because now we can potentially decode any character in any language with only one neural decoder for hand trajectory. It means that you can write in English, Hebrew, Mandarin, or even monkey language, and we can understand you wanted a banana. So there are many challenges ahead of us to improve functionality and speed. And I want to hand it off to Bliss to talk about the third part, how we are making our brain interfaces work anytime, anywhere.
Hello, everyone. My name is Bliss, and I'm a software engineer here at Neuralink. When I use my computer, my mouse and keyboard work how I intend them to, at least like 99.9999% of the time. My goal is to enable a user with paralysis to control their computer as reliably as I can. Here's what we want that experience to feel like. In this video, you can see Saki walking over to his MacBook and choosing to work on his typing task. The entire decoding system works out of the box, and it feels totally plug and play. The first step to achieving this kind of high reliability is to test extensively offline. A typical flow for using the N1 link is to connect over Bluetooth, stream out neural activity from the brain, and then use that neural activity to train decoders and do real-time inference. We've built a simulation for exactly this sequence, but instead of using a monkey with an implant, we use a simulated brain that injects synthetic neural activity into an implant sitting in a server rack. From the point of view of that implant, it's in a real brain. This simulation runs on every code commit to validate that from the hardware all the way up through to the neural decoders, our entire stack can achieve state-of-the-art performance. However, while this kind of simulation is great for integration testing of software and hardware, it's not yet detailed enough to guarantee high reliability in the real world. In the real world, the underlying signals we're trying to decode actually change day to day. In this plot, you can see the average firing rate detected on a representative channel of Saki's implant. Each bar represents one day, and you can see that each day has a different average firing rate than the previous. This presents us with a very interesting problem for how to make our decoders robust day to day. It can actually happen that if you train a neural decoder on one day of data and then try to use it on the next, the average firing rates can actually shift enough to cause a bias in the output of the model. Here on the right, you can see that this bias is making it hard for the cursor to move to the upper right corner. You see it struggling here to make it up to the upper right, and then it moves much more effortlessly down to the bottom left. We're trying many approaches to mitigate this problem. Some examples include building models on large data sets of many days of data to try to find patterns of neural activity that are stable across days. Another approach we're trying is to continuously sample statistics of neural activity on the implant and use the latest estimates to pre-process the data before feeding it into the model. This is really an active area of research for the team, and it's a critical problem to solve if we want to enable someone with paralysis to control their computer as well as I can. Another big problem we have is to minimize the time it takes for a spike in the brain to impact the movement of the cursor on the screen. If you have lag or jitter in this control loop, the cursor becomes hard to control, leading to the kinds of overshoots that you can see here on the right. One big improvement we've made towards in this direction is called phase lock. Phase lock aligns the edge of each packet that we send off the implant to the exact moment that the Bluetooth radio is going to wake up. This minimizes the time it takes for a spike in the brain to be incorporated into the prediction of our neural network. Here you can see the latency distribution after phase lock. Not only has the mean been greatly reduced, but the variance has been reduced as well. This makes it easier for the user to predict the behavior of their cursor. Over the last year, we've made tremendous improvements to the stability and reliability of our system. And we've been able to demonstrate consistent high performance across many sessions and many months. However, there's still a long road ahead of us before the system will truly feel plug and play. So if solving the hard problems required to ship this technology is exciting to you, you should consider applying to join the team. Now, I'm going to hand it over to Avinash to talk about how our custom low-power ASIC detects spikes in the brain.
Hi, I'm Avinash, one of the engineers on the ASIC team. We designed the custom neural sensors, which include both analog and digital circuitry, to record and stimulate across 1,024 independent channels. We face challenges across all three major metrics: performance, power, and area. Not only do we have to fit all 1,024 channels into a single quarter-sized implant, but we also have to measure spiking activity less than 20 microvolts in amplitude. And today, I'd like to focus on the last challenge I mentioned, power. Power consumption is important to us because we want to give future users a full day of use of their implant without any interruption for charging. Back in 2018, we were sending every sample from every channel off the device for processing, which burned a ton of power. In 2020, we brought spike detection onto the chip.